Who's a hockey fan right now? What do the Calgary Flames right now, okay, not for the year, but what do they have right now in common with this train that's barreling down this track? Anybody know how the Flames have been doing lately? They won 3 games in a row. That's a pretty good one, actually. Well, they're back on the rails right now because they've won 3 games in a row. What do the Flames right now, as they just played Chicago and won, what do they have in common with the train? They have momentum. They have momentum. Okay, and what do we say? What do we think that momentum really means, right? When we talk about that train and we talk about the Calgary Flames having won 3 games in a row, what do we think of when we associate that momentum with the Flames and with that train? What is it exactly that they have in common? In other words, what is momentum really? What does it really mean? When a team is winning lots, it's what? It's hard to stop them. Right? It's hard to stop a team that's winning lots, and it's hard to stop a train that's moving as well. They both have momentum. That's how we define momentum, or at least that's how we think of momentum. That's not the real definition of momentum, but that's what it really means, how hard it is to stop something. Now, in Physics 30, we're going to talk about this kind of momentum, right? Real physical momentum, not sports momentum, not psychological momentum, right? It's hard to stop these guys because they're confident, they've been winning, okay, so on. But in the end, we want real physical momentum. That's what we want to talk about here. What is it that provides real physical momentum to a train? In other words, what makes it difficult to stop a train that's moving down the tracks? There's a couple factors. What makes it difficult, Patrick, to stop a train that's moving down the tracks? Speed and mass. The heavier something is, the harder it is to stop, right? The faster something's moving, the harder it is to stop. A few years ago, it's probably 6 or 7 years ago now, actually, my wife and I had gone out. At the time, we had one son. He was 4 or 5 at the time. We had a babysitter at the house. On our way back home, we had to stop at the bank to get some money to pay the babysitter. Okay, the bank that we went to at the time was down beside the town office, across from the town office. It was the Royal Bank at the time, down there. So we pull in, okay, right beside the town office. I run across the street. I get money out of the bank. I come back. I get in the car, and then I start driving forward to go across the tracks. Right? You guys know where I'm talking about? To go across the tracks. I stop because the lights come on, and there's a train coming down the track. So I stop. I'm like, I don't want to wait 5 minutes to go across these tracks and to go back home. So I turn down that alleyway behind the town office. Okay, and as I turn down that alleyway behind the town office, the train goes by, and it's all good. Then I turn around. Okay, I pulled into the hi-ho to get some change, like to change my 20s for smaller bills. Okay, and then I came back out, and I came by the town office again and realized, well, the train has stopped. The train has stopped on the tracks. And the reason the train was stopped is because the guy behind me that was driving right behind me as I was waiting for the train, I turned down the alleyway. He just decided he would cross the tracks. But he didn't make it across the tracks. He got hit by the train as he was trying to cross the tracks. The train wasn't going that fast. It was going right through town. But I saw this guy's minivan. It was 300 meters down the track. Literally, the train in his minivan was 300 meters down the track. Why? The train wasn't moving fast. Why was the train and the car 300 meters down the track? Train had a hard time stopping, right? Why did it have a hard time stopping? Because it had lots of momentum. And why did it have lots of momentum? Because it was not big, heavy. Right, it was heavy. It had lots of mass. Now you can imagine if it's moving fast, it's going to have even more momentum. It's going to be even more difficult to stop, right? 2 things make it difficult to stop. 2 things give it momentum. The 2 things that give it momentum are the mass and the velocity. And because we define momentum It's how hard it is to stop something, and how hard it is to stop something is based on its mass and velocity. It comes back to the real definition of momentum, which is the product of mass and velocity. Bigger the mass, bigger the momentum. Bigger the velocity, bigger the momentum. Now we're going to differentiate that with inertia that you learned about a little bit in Physics 20. Inertia is not how hard it is to stop something, but it's real close. Momentum and inertia are really similar to each other, but not the same thing. Does anybody remember what inertia is? Tanner? Yes, you're real close, actually. Tanner said an object's want or tendency to stay in the same direction as it's going. Yeah, that's part of it. It's the tendency to keep doing what it's doing, to keep going in the same direction at the same speed, right? Well, how's that different then? If it wants to keep doing what it's doing, if it's moving and it wants to keep moving, then how is that different than how hard it is to stop something? The big difference is that inertia is related to mass only, not velocity. If an object is moving, it wants to keep moving. If an object is at rest, it wants to stay at rest. So inertia is certainly related to momentum. The heavier something is, the more momentum it has, the more inertia it has. But momentum is also dependent upon how fast it's moving. Inertia isn't. Inertia is simply dependent upon its mass. We'll just say that this is the tendency to keep doing what it's doing. And we'll say that it depends on mass, not mass and velocity like momentum does. So let's take a look at these two trains that we see on the tracks right here. The first one is the train that was moving down the tracks, not very fast, but moving down the tracks. The second one is a train at a train station. It's stopped. It's not moving. Can you tell me which of these two trains has momentum? The one that's moving, right? It has momentum because it's got mass and because it's got velocity. Tell me which of these two trains, in other words, it's this one, right? This one has momentum. Does this one have momentum? No, it doesn't because it's at rest, right? Tell me which of these two trains has inertia. They both do. This one's moving and it has mass. This one's at rest and it has mass. The mass is the only thing that's important there, so they both have inertia. Does that make sense? Okay, momentum versus inertia, almost the same thing, not quite. Momentum is a vector because it depends upon mass and velocity. And velocity is a vector, right? You guys remember what a vector is? It has magnitude and direction, right? Despicable Me. You guys ever watched Despicable Me, the movie? There's when the villain Vector is going into the villain bank to get his loan. You guys remember that scene? Talks about his name is Vector. He has both magnitude and direction. Right? Momentum is a vector quantity as well because it depends upon direction. The equation, well, we already said that it's defined as a product of mass and velocity, so it's going to be equal to m times v. The symbol for momentum is a lowercase p. Power is a capital P. Momentum is a lowercase p. Power doesn't have the little half arrow over top of it. Momentum does have the little half arrow. The units for mass are going to be kilograms. The units for velocity are going to be meters per second. And the units for momentum are going to be Travis? You're real close. I think you were thinking the right thing, just didn't quite say it right. Not kilograms per meters per second. It's kilograms times meters per second, right? Per is a division, right? So it's kilograms times meters per second. That's kind of an odd set of units, right? It's kind of odd that we don't have something like, energy is a joule, right? We replace kind of funny units with a joule. We don't have something like that for momentum. Okay? There is another set of units that you'll learn for momentum later on, but it's not much nicer than that one. So for now, we'll go with this. Kilograms, meters per second. So let's make sure if our mass is in grams, we convert it to kilograms. Let's make sure if our velocity is in kilometers per hour, we convert it to meters per second. How would we, by the way, convert grams to kilograms? Because that's something we have to do fairly often. Multiply by 1,000. You ever forget? Like you ever think like, geez, I know it's 1,000, but is it multiply or divide? Anybody ever forget that? I do. Not necessarily for kilograms and grams, but for lots of conversions, I do. You know what I do when I forget? I guess. But then I check my guess, right? Let's say I guessed. Multiply by 1,000. Okay. Let's say we had. Let's say I was making pasta last night, and I put ground beef in my pasta, and I wanted 454 grams of ground beef. That's a pound. Okay? So I put 454 grams of ground beef in my pasta last night. I wanted to convert that to kilograms. So let's say I forgot and I multiplied it by 1,000. 454 times 1,000 is a lot of ground beef. 454,000 kilograms of ground beef. That's a lot of cows. It's not multiplied by 1,000 because that's not a reasonable number, right? Check if you have to guess, that's okay, but check it. Clearly, it's not multiplied by 1,000. Clearly, it's going to be divided by 1,000. What about our speed, our velocity here? Let's say we do have to convert kilometers per hour to meters per second. What's our conversion? Yeah, you multiply by 1,000, you divide by 3,600. There's a shortcut that I'm going to teach you right now if you haven't heard it already. Anybody know what that shortcut is? Divide by 3.6. And it always works. The problem with that is sometimes people forget and they multiply it by 3.6. But again, that's okay as long as you stop and you consider whether your answer is reasonable. Okay, I'm traveling down the road at 100 kilometers per hour. That's a reasonable speed, right? 100 kilometers per hour? Unless you're Justin Bieber drag racing in a residential zone with their rented Lamborghini. He's 20 years old, isn't he? How does he even rent a car? Don't you have to be 25 to rent a car? I don't know. 100 kilometers per hour is usually a reasonable speed. Okay, traveling down the highway. Let's say I want to convert that to meters per second, and I forget, and I multiply it by 3.6. I get 360 meters per second, right? That's faster than the speed of sound. Is that reasonable that I'd be driving down the highway at faster than the speed of sound? No, it's not. So I guessed wrong. So now instead of multiply by 3.6, I divide by 3.6, and I get something like 27 meters per second. Is that more reasonable? Sure, it's still fast. 27 meters in 1 second, 3 times the length of this classroom in 1 second is still fast. That's why you're not supposed to speed through school zones, because you go a long ways before you can stop. But it's not 360 meters per second. It's not faster than the speed of sound. Kind of fast. All right, we're going to do a quick example here that's going to use that equation that we just learned. And this is on page 451 of your textbook. It's in chapter 9, 9.1. You do not, as we're doing these, need to write down the questions. You have the questions. Just reference it. Okay, when you're writing things down, write down 9.1, page 451. And then write out the solution. Okay, everybody in this room, whether you think you're so smart and don't need to do it or not, whether you have a computer or an iPad or not, whether you've downloaded the notes already or not, doesn't matter. Okay, everybody should write down the solution as we're doing a question here. 180 kilogram bumper car carrying a 70 kilogram driver has a constant velocity of 3 meters per second. What's the momentum of the car driver system? I don't really care about this last part here. Draw the momentum vector. I don't care about that. That's not what we want to do here. First thing we do, What do we always tell you in Physics 20, the first thing to do here? Write down the givens, right? Write down the givens. Okay? Don't do that first. Don't do that first anymore. Okay? What you need to do now is consider big picture. Okay, what are we dealing with here? What kind of concept are we dealing with? And then let's worry about our givens. You know what happens if you write down your givens first? You get tunnel vision. You look at numbers and you don't look at the big picture anymore. And in Physics 20, we can get away with that. Okay, we can't get away with that in Physics 30. We need to look at big picture. Now, givens are important. They're really important. Okay, but big picture is more important. Okay, what concept are we dealing with in this question? It's momentum, right? I mean, there's only one thing we've learned, right? It's got to be momentum. So it's going to be a P equals M times V problem, probably, right? Because it's momentum. Even though we haven't written down our givens, we probably know that's what we're going to do. Now, we got a couple choices. We've got to write down our givens here. We can write them down the old-fashioned way. M is equal to this, and V is equal to this, and that's okay. You can keep doing that if you want. Or we'll let you do this now. If you have them printed off in front of you, you can just circle them if you want. Okay? But don't just circle them and leave it. Circle them and write down what it is. We know it's a momentum problem. We know we have mass and velocity. By the way, why did we use both of those masses instead of just one of them? We're trying to find the momentum of the system, not the momentum of the bumper car or the driver, right? Momentum of the system. Okay, we've got the mass, we've got the velocity. We know we're going to use this equation because we already identified that that's my concept. M times V is 250 kilograms times a velocity of 3.0 meters per second. They have already defined east as positive for me. So we'll make it positive 3.0. Multiply those together, we get 750 kilograms meters per second. Final answer? No, it isn't. What is my final answer? Okay. East, yeah. But since we've defined positive, it's probably okay to leave this because it's a positive answer, which means to the east. Travis? Yeah, significant figures. How many digits should we have in this answer? We should have 2, right? Because this is 3 digits, this is 2 digits, this is 2 digits. We always go with our least precise. .5 times 10 to the 2 kilograms meters per second. And if you add in that it's to the east, then that's great. That's okay. But since we defined east as positive, it's okay not to do that too. Well, Physics 30 is easy, isn't it? Wow. Could you see a question like this on a unit test? Sure. On a diploma exam? Sure. We're done like 2% right now. Physics 30. How does that make you feel? We're done like 2%. If we wrote a diploma exam right now, you could make 2% on it. Does that make you feel good? All we need to do is get another 80 or 85%, and we're good to go. Okay? I'm going to have you right now, just so that we can make sure that you're okay with this concept, work on a couple other questions here. Question 1, you can skip 1B. But the rest of it I want you to do here. We'll give you a few minutes to work on this in class here. See what you can do, and then we'll take a look at one or both of these questions as a group if we need to. Right? If we're not having any trouble with those 2 questions, then let's move on to one more question that's not in your textbook. This will be the last example that we do here today. This one says a 1.5 kilogram object falls from a height of 14 meters. What's the momentum of the object as it hits the ground? Now, again, before we look at our givens, okay, let's take a look at what's really going on here. What is going on here? We want to find the momentum of this object as it hits the ground. But before it hit the ground, it fell. So we're really dealing with 2 things here, right? We're dealing with a momentum problem as it hits the ground, but we're also dealing with, before that, a falling problem. An object falls down, right? That's 2 problems, really, right? Something happens, then something else happens. Okay, it's important that we look at it that way as opposed to, just looking at the numbers. It's important that we look at it that way because if we just look at the numbers, we're probably not going to notice that it's really two problems. Okay, we're going to forget, and we're trying to make it into a one problem, a one equation problem, most likely. So let's look at the two separate problems. Let's look at the fall, and then let's look at the collision with the ground. Okay, the fall, well, we know the mass is 1.5 kilograms, whether it's falling or whether it's in the collision. We know that it falls from a height of 14 meters, so its displacement as it falls would be negative 14.0 meters. We want to find the momentum as it hits the ground. I didn't circle my givens in this case simply because it was a two-step problem, and I kind of thought it was a little bit easier to write them down as opposed to circle them. I just think it's a little bit neater that way this time. We want to find the momentum as it strikes the ground. We're going to say m times v. Okay, that's what we do when we want to find momentum. The mass is still 1.5 kilograms, but we don't know what v is. Do we have a way to find that? Yes? How? Okay, so we know the acceleration here is also negative 9.81 meters per second squared. Yeah, we are going to use that. You're right. We're going to use that along with some other equation, right, Travis? No? You guys know this? There's a couple ways you could do it here, by the way. Yeah, you do. Yeah, you do. You guys remember this? Vf squared is equal to Vi squared plus 2a delta d. Let's get Vf. Vi is 0, right? Because it falls, actually says it falls from a height. It should say it falls from rest. That's what I meant. It's the square root of 2 times a times d. 2 times neg 9.81 times neg 14. Let's get that number. Let's say 2 times neg 9.81 times neg 14. And then let's square root that. And we get 16.5735. Notice I went to 4 decimal places here because that's not my final answer, right? If it's my final answer, I round it to the right number of significant figures. But try to go to as many decimal places as possible when it's not my final answer. Now my momentum is equal to m times v. What's v? 16, right? 16.5735, right? Not quite. Not quite. What did I solve for up here? What number is this? What does that mean? That's the final. No, it's not the final velocity. It's the final speed. What do I need right here? I need the final velocity. What's the velocity? Not 16. It's negative 16, right? Does that make sense? Multiply those two numbers together now. And we end up getting 24.86. Where are we going to round that to? Negative 24.9? Is that the right number of digits? Looks like it. You could say neg 24.9, or you could say 24.9 down. Either one. Do you see the value in looking at big picture here first in this question? More so than the last question, right? Okay, looking at what's going on here before we look at what are we given. Okay, what's going on? We have a fall, and then we have a collision with momentum. Okay, that tells us that we've got to do two problems here, not one. If we just look at givens, some of us are still going to do it right. But some of us are going to try to find one equation that works here. and forget to do the other one. Okay? We're going to take a look at multiple choice now, question number 1 that appears on page 11 of the booklet that I handed out to you at the beginning of class. I'd like you to submit that, please, electronically as multiple choice number 1 on that form that I showed you. Okay, multiple choice number 1. Submit that when you're finished. Okay, if you don't have a computer or an iPhone or whatever to submit it, then just get your neighbor to submit it for you after they're finished. All right? Give you a few minutes to work on that one right now. All right, so we've all got, or most of us have answers submitted here. Taking a look at what we picked here, kind of all over the place, actually. 11 people picked D. We had, which is only 48% of you, picked D. 22% picked C, so quite a few of you picked C. 13% picked A. 9% picked B, and then 9%, they just weren't sure. They picked option E. They weren't sure. So most of us picked D. Let's see if B is actually the correct answer here, okay? Batter hits a fly ball. The .13 kilogram baseball moves at a rate of 20 meters per second at a point where it's 5 meters above the ground. What's the magnitude of the momentum the instant before it strikes the ground? How many people did this? How many people looked at this and said it's a momentum problem, P is equal to M times V? And then they said 0.130 kilograms times the velocity of 20 meters per second gives us 2.60 kilograms meters per second. I'll tell you how many people did that. %22 of you did that. Why is that wrong? Why did 22% of you choose C, the wrong answer? Yep. Good. This is the perfect example of why we should look at big picture as opposed to just look at givens, right? Okay, we start looking at givens here. Oh, look, we got a mass, we got a velocity. Perfect. M times V is 2.6, but it's the wrong answer. When we look at big picture here, we see that, yeah, we're trying to find a momentum when it hits the ground, but it's falling from a certain height, just like that last example was, right? It's falling and then it hits the ground. It's the same question pretty much as we had just a few minutes ago for our example here. So let's look at givens in two situations here, in two spots, falling and then the collision with the ground. Okay, when it's falling, well, it's got a speed there of 20 meters per second. It's moving at a rate of 20 meters per second when it's 5 meters above the ground. It falls negative 5.00 meters. And of course, its acceleration, just like in the last question, was neg 9.81 meters per second squared. We want to find the momentum as it strikes the ground. So basically, we want to find its final momentum. It's m times v. But in order to do that, we're going to use vf squared is equal to vi squared plus 2ad in order to get vf. This time it's not 0 for vi, it's 5. 5 squared plus 2 times neg 9.81 times neg 5. And we square root that. Sorry? Oh, sorry. Yeah, you're right. Yeah. Thank you. The initial speed is 20, right? What do we get for VF there? 22.3? 22.3 what? No, let's keep going on more decimal places. 3184. Okay, 4 decimal places is good. Now that we have the final speed, we can convert that to a velocity and then multiply it by m. Now it's 0.130 kilograms times negative 22.3184. And I'm pretty sure when we do that, we end up getting neg 2.9, right? Why do they put the answer as 2.9 then, not neg 2.9? No, not because it's instantaneous. They're asking for the magnitude of it, right? And the magnitude doesn't include the direction, right? So we got the direction. We didn't really need that. Okay, they're asking for just how big the number is. Does that make sense? Okay, big picture, right? Big picture. Okay, let's look at big picture before we look at givens. Givens are important, really important. Big picture is more important, especially when we get a question like this, all right? Oh, perfect timing. Here's your homework for tonight, guys. Worksheet number 1. Homework is worksheet number 1. There's probably a pretty good chance I'm going to check that homework tomorrow. Okay, well, I will go over it tomorrow. Pretty good chance I'm going to call you up to my desk to make sure you have it done. Okay, have it done. If it's wrong, that's okay. Just do your best. That's all I expect. Do your best on it. Have a good night, guys, and we'll see everyone tomorrow.